All right, let's dive in. Today, we're going to break down one of the most fundamental ideas in all of data and statistics, probability distributions. You can think of them as the secret blueprints for understanding chance itself.
So think about it. From the number of sales you make in a day to the heights of professional basketball players, how do we actually model and make sense of all the uncertainty that's just everywhere? Well, the answer is this incredible tool called the probability distribution.
So here's our game plan. First, we'll split the world of data into its two main families. Then we'll take a quick look at distributions for data you can count. That's discrete data. After that, we'll do a deep dive into the ones for data you measure, which is our main focus today. And finally, we'll talk about why all these different shapes matter so much.
Okay, first things first. We absolutely have to understand that data really comes in two basic flavors, discrete and continuous. And trust me, getting this difference is the key to everything else we're going to talk about.
So on one side, you have discrete data. These are things you can literally count in whole numbers, like the number of sales you make, or the number that comes up when you roll a die. It's going to be 1, 2, 3, 4, 5, or 6, nothing in between. But then you have continuous data. These are things you measure. Someone's height isn't just 6 feet or 7 feet. It can be any possible value within that range. Same thing for the time it takes to run a race. So one is counted, the other is measured. Simple as that.
All right, now that we've got that difference down, let's do a quick tour of some common distributions that were built specifically for that countable, discrete data.
First up is the uniform distribution. Super simple. Every outcome has the exact same chance of happening, just like rolling a fair die. Then you've got the Bernoulli distribution, which is just a single event with only two outcomes. Think yes or no, true or false. Now, if you do that Bernoulli trial over and over again, like flipping a coin 10 times to see how many heads you get, you're now in the world of the binomial distribution. And finally, there's the Poisson distribution, which is awesome for counting how many times something happens in a set amount of time, like how many customers walk into your shop every hour.
Okay, now let's make the jump into the continuous world. And we have to start with the most famous, the most iconic distribution of all time, the normal distribution, which you probably know as the bell curve.
You know, the reason it's called normal is because so many things in the natural world just seem to follow this pattern. It's that perfect, symmetrical bell shape, where most of the values are clustered right around the average. For instance, if you measured the height of every single NBA player, most of them would be pretty close to the average height. You'd have very few who are super short and very few who are incredibly tall. The same thing happens with the weight of adult polar bears. Most of them are right around the average, and the outliers are pretty rare.
Now that bell curve is great if you have data for all the NBA players or all the polar bears. But what happens when you don't? What if you've only spotted, say, 10 polar bears in the wild? Well, that's where this next distribution becomes an absolute lifesaver.
Meet the student's T distribution. It's basically a cousin of the normal distribution, but it's specifically built for when you're working with small amounts of data. Its secret weapon? It has fatter tails. Now, all that means is that it gives a little more probability to extreme outlier results. It's a way of saying, hey, we only have a small sample, so we have to be more cautious and accept that wilder outcomes are more possible. This table just lays it out perfectly. You use the normal distribution when you have tons of data and less uncertainty, but you use the student's T when you have a small sample and you need to account for more uncertainty by design. And what's so cool is that as you collect more and more data, the student's T distribution actually starts to morph and eventually becomes identical to the normal distribution. It literally adapts to how much you know. So far, we've seen these nice, symmetrical, bell-shaped curves. But let's be real, data isn't always that neat and tidy. So let's look at a really powerful tool that's built for asymmetry, the chi-squared distribution.
Now this one is a bit different. It only works with positive values, so its graph is always skewed to one side. You're not really going to use it to model something like polar bear weights directly. Instead, this is a statistician's best friend. They use it to test their theories, to ask the question, how well does my model actually fit the real-world data I've collected? It's all about measuring that goodness of fit.
Distributions aren't just for static measurements either. They can model processes that change over time and even help us predict success or failure. So let's check out two final, super useful types, the exponential and the logistic distributions.
The exponential distribution is perfect for modeling things that have a huge burst of activity right at the start and then quickly fade away. A perfect example is a new article online. It gets a massive flood of clicks in the first few hours, but then interest just drops off. On the other hand, the logistic distribution is all about forecasting. Think about an e-sport like Dota 2. Analysts can use this to figure out the exact tipping point, like how much of a gold advantage does a team need at the 10-minute mark to be able to predict with confidence that they're going to win the whole match.
Okay, we have thrown a lot of names and shapes at you. Normal, students t, chi-squared, but let's get down to it. What's the real takeaway here? Why do these shapes actually matter?
Here's the bottom line. These aren't just abstract math concepts. They're the language we use to understand a world that's filled with randomness and uncertainty. Knowing the right shape to use allows us to find meaningful patterns, to make much better predictions, and to really test if our ideas about how the world works are actually true.
And that brings us to a final question for you. From the amount of time your commute takes every morning to the number of emails that hit your inbox every hour, our lives are absolutely governed by these hidden mathematical patterns. So take a look around. What unseen distributions are shaping your world?